All right, guys, kind of the first thing we did in unit 6 was that we looked at sort of like what does an integral mean? And it was like the area under the curve, and we did some Riemann sums, and then we got a little bit closer to the true area when we used trapezoids. And then we actually started integrating, right, and using integral rules. So just kind of like taking you guys back there. This is all pretty much kind of like a level 1 big kind of pie in the sky overview. So this very first multiple choice question is no calc, and it's asking for a left-hand Riemann sum. When I'm thinking about, when I'm thinking about Riemann sums, remember that we have midpoint left and right, and we usually see this as RL, so that's a Riemann left, a Riemann right, or a Riemann M. So we're kind of remembering that, like, seeing those a lot of different ways and like kind of notating which one you're using is important. Then the other thing when we are doing this is like a right Riemann sum is we use that right endpoint, right? So we're using this. And we also talked about like when is it an overestimate, when is it an underestimate. So this was a right. And remember, if the function is increasing, the right point is always going to be an overestimate, which makes sense because it's because that right point is always going to be higher. That left point was using that left value. So like if you were to make that pillar like a left hand and a right hand of the pillar, using the left hand. And so this is the left, and in that middle, you guys can probably figure that out pretty easily. It was in the middle. So remember that concavity really only impacts trapezoidal sums, and it's increasing or decreasing that impacts right and left. So remember, if it's increasing, that's an over. If it's decreasing for right, that's an under. If it's increasing for left, that's an under, which makes sense because the left point will be lower. And if it's decreasing, that left point will actually be higher, right? Because everything to the right is going to be smaller. So that's going to be an overestimate. And then the trapezoidal. So trapezoidal, let's see if I can spell this right, boy. A trapezoidal was when you actually made that trapezoid. And remember, those trapezoids are both increasing and decreasing depending on what's happening. And if it's concave down, the trapezoidal would be an underestimate. And if it's concave up, you're actually kind of creating these lines here, right? So we're saying like, okay, this is an overestimate if it's concave up, because we're kind of creating those like secant lines in a way where that concave down is like that chord. So let's go over here. A lot of information. We're actually not looking at trapezoidals in these 3 problems, but it's kind of good to keep in mind. In these 3 problems, we're looking at like some integration rules and then that left-hand Riemann sum. So a left-hand Riemann sum of 3 subintervals. So usually your tables are done pretty well where you have like, okay, here's going to be 1, here's going to be 2, there's that second rectangle, and then that third. Always, 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 if it helps, draw it out. So you can be like, okay, what's going on here? I know it's 0, my output's 5. At 2, my output is 2, so 1, 2. 1, 2. At 4, my output is 8. And then at 6, my output is 3. So what we're doing here is we're taking that left-hand Riemann sum. And this looks like it's probably a curve. I don't know. But that first rectangle is going to be this pink guy right here. And we're going from 0 to 2, but we're using that left-hand value. So that left-hand height. So when we do that base times height, so there's that Riemann sum left, this is going to be that base, that is a distance of 2. The height is that left-hand value, which is 5. That next rectangle, we are going from 2 to 4, but we are using that left-hand value for the height. So this one's going to be a pretty drastic underestimate. We still have a width of 2, but in this scenario, our height is that y value for my left term. I'll actually use a blue for this last rectangle just to get a little bit of color differentiation. This guy's going to be a pretty drastic overestimate because between these two, I'm going to go all the way up to that left-hand height of 8. My width is still 2, but my height in this scenario is 8. And of course, you don't need a calculator for this because this is pretty straightforward. So you have 10, 4, and 16. And you add those together, and you should get that this is going to be 30. Because this was acceleration, remember Riemann's sum is a form, an informal integration. So an integration takes that acceleration up a notch. So remember our acceleration goes to velocity because that's the integral. So this goes from feet per second squared to just feet per second as the unit. So we are looking at B, 30 feet per second. Next guy here. We are now moving. Both of these are calc okay. Looks great. The graph of f is shown in the figure above. If 1 to 3 of f of x, great, love that they're giving us this. It's an ugly curve. Is 2.3. I'm going to actually highlight this. We are like, okay, cool. This makes sense. So that area is going to be 2.3. I'm going to actually write that in here. And f prime of x is f of x. Cool. And we want to know f of 3 minus f of 0. All right, so we are looking at that f of 3 minus f of 0. Here's where those integration rules are like kind of nice here, because what we're saying is we know that if f prime is f of x, right, then that means that f of x is going to be the integral of lowercase f of x. So right here, what we're really saying is we want to be substituting. We're really finding the integral from 0 to 3. So we want to know, let's use some integral properties. I'm going to substitute that in. Integrating f of x, capital F of x, and we are evaluating over the area from 0 to 3. So that's going to be f of 3 minus f of 0. So just kind of like working out what it's actually asking, which is really what's the area between 0 and 3. Well, we were already told that that yellow piece is 2.3. I'm going to shade this green because that's the piece we don't know. We just need to add that little piece in. This is a rectangle, so it's length times width, which is 2 times 1, or 2. So this is really just going to be 2 plus 2.3 for an area of 4.3. And we're good to go. Last one here. The regions A, B, and C in the figure above are bounded by the graph of the function f in the x-axis. If the area of each region is 2, what is the value of negative 3 to 3? F of x plus 1 dx. Okay, so we're going to break this up into two integrals. We know this is the same thing as negative 3 to 3 f of x plus negative 3 to 3, 1. Let's get those dx's. My apologies, because those are all derivative functions. We know that all these areas are 2. I'm going to actually put a negative 2 in A and C because they're both below the x-axis, and then I'm going to put a positive 2 in B. So getting this guy done, I'm just going to say negative 2 minus 2 plus 2, a little bit of a tongue twister, so that's a negative 2. This guy's a little trickier, but not too bad. We're just going to integrate. You know the integral of 1 is 1x. You could also use that integral rule, saying that it's just going to be 1 times 3 minus negative 3. It's going to be the same thing, and you'll see here. And we're evaluating that from negative 3 to 3, which gives us the exact same thing. We're plugging in that 3, so 3 minus negative 3 gives us that exact same thing as earlier. So I have negative 2 plus 3 plus 3, so 9 minus 2, and that gives us a positive 7.